Okay, so here we're doing applications called finding the differential. It's really not too much more than doing a derivative of the expression and then including the chain rule. So in a lot of these, there's like multi-step chain rule, but at the end, you all need to also include dx. It's used a lot in things like linear approximation and finding like the errors of things. So we're going to do 23 as an example. When we do derivatives, it's usually easier, instead of writing it in radical form, to write it as a exponent. So this would be 1 minus x squared to the 1/2, right? And now we can actually start doing the derivative. We get the expression from the power rule. We pull out the 1/2. We leave the inside alone. We get 1 minus x squared to the negative 1/2. Now we finish off with the derivative on the inside, which is 1 minus x squared, so we get a negative 2x. And then the derivative of that would simply be dx. And that's very important when you're doing differentials, because you're going to have to calculate that eventually. If we cancel out the 2 here with a 2 there, we end up with negative x over the square root of 1 minus x squared, and then you multiply by dx. If we do something like 25, so here we're dealing with arctan. The derivative of arctan of x, if you remember from earlier, it's 1 over 1 plus x squared. And so when we're doing the derivative or the differential of arctan of 4x, that's where we're actually going to begin. But again, it's a chain rule, so we have to start with this expression. So we take 1 over, and since our argument is 4x instead of x, we get 16x squared because the entire thing gets squared. Now we're going to multiply by the derivative of 4x, so that's 4. And then we're going to also include a dx. So you end up with your final expression is 4 over 1 plus 16x squared dx, and that's your final answer. You can use that to find linear approximation or errors